Hello friends, welcome back to my YouTube channel MS Maths. In this video, we are going to discuss about the concept of measure and integration theories, basically the almost everywhere. So what is the almost everywhere? Almost everywhere is a concept in which we'll just discuss the concept with the example. Okay, if we have two function defined on AB, okay, this is the closed interval and two function defined on AB. If f and g almost everywhere and the functional values are not equal, see the function f and g are almost everywhere, it means all the values will equal but not almost everywhere but not equal. Okay, it means the measure of this is basically zero. यानी कि it means for all x, it means for all those x for which the functional values are not equal, then it will be the measure for that particular set is basically zero. Okay, it means the measure is non-zero for all those x on which the function x and g are equal. Okay, same thing is here. If f is convergent on AB almost everywhere, it means f is not convergent for all those x of the interval AB. For that f is not convergent, so that measure of that particular collection of x is equals to zero. Okay, if a sequence is converging to f, and if a sequence is converging to f almost everywhere, so the measure of all those x of the interval AB for which the function or the sequence fn does not converge for f. Okay, so basically if f is, or basically a function is almost everywhere, so the condition that satisfied by the function, or all excluding x, or all those x which is not satisfying the condition for the function is satisfying for all x or everywhere x, that is basically, or the collection of that set and the measure of the collection of that set is basically the zero. This is the concept of the almost everywhere. Okay, so yeah, next we'll start. So next we have a simple function. Simple function is basically a non-negative, a non-negative finite valued function f of x taking only finite number of different values. It means that the range set of the function is what? Finite. It means it will contain the finite number of element in its range. Okay, so the characteristic function is basically the example of simple function. It means it will contain one only, or finitely one for this x. If x belonging from E, then it is 1, and x is not belonging from E, it is 0. It is what? The characteristic of the set or the function. Okay, if a1, a2, an are distinct values, then it will be basically ai. Then, like, that is basically the range set is ai is equals to some a, such that phi of x is equals to ai. So it is finitely. Then clearly that the sum of all this is basically the function. It means we can conclude that phi of x is what? Summation I is equals to 1 to n of all those elements which are in the range. It means that is ai. So that is chi of ai of x. This is what the range, or it will be equals to the function. Now the set ai are miserable if and only if phi is miserable. So this is the definition, or this is also we have basically, yes. So I have to explain this one. What is this result? Says that, yeah, AIs are miserable if the function is miserable. It means that what is AI? AIs are basically the set in which the range set contain, in which the element or the range element will contain. So this is basically what AIs are miserable, then function is miserable, where AI intersection AJ is equals to phi. It means where I does not equals to j. Okay, and the union I is equals to 1 to n of all ai is what? Real number. So these are the property of the set AS. Okay, now next we have some definitions, that let phi be a non-negative simple miserable function. It means it contains the finite number of element in its range. Then the integration of phi is what? The summation I is equals to 1 to n ai, and the measure of a, where a is what? The element or the x for which the set, it is the set in which the elements are the range. Element are from the range set. Okay. For any non-negative measurable function, the integral of function is basically f dx is nothing but supremum over the phi less than f. Okay, phi is less than f of the integration phi of x. So it is what the function f of x, integration of function f of x. Okay, it can be defined as, yes, it is the integration. It means the integration of f is what? The supremum of integration of phi of x, where phi is less than f. Yeah, this is the definition of the integration of f, where f is a simple integrable measurable or non-negative measurable integrable function. Next, where supremum is taken over all measurable functions, all simple measurable function, those which are basically I less than for which I less than f. Okay. Now the definition third is basically for any measurable set e and any non-negative measurable function f. So if we integrate f over the measurable function e, then it will be equals to the characteristic of that function on which we are integrating, on which measurable function we are integrating. It's basically f into the characteristic of that center. Okay, so this is what the definitions. Now we are going to prove some result. What are the results? So first, we have some remark is basically, what is the remark? If AB is in closed interval, then the interval, the integration over E f dx is what? A to B f of x dx. First one is this, and second one is if A is greater than B, then A B f of x dx is what? Minus of AB f of x dx. These are the just properties of the integration. Next, theorem. What is the theorem for this? Theorem is basically this. If the statement of the theorem, theorem number one, if phi is a simple measurable function, then with usual notation, first e, the integration over e of phi dx is basically the sum of I is equals to 1 to 1 to n ai, the measure of ai intersection en. So this is for what? For any measurable set E. Okay, where E is any measurable set. The next result is basically the integration over A union B I dx is equals to A phi dx plus B phi dx. This is for A union B is equals to phi. It means these both are disjoint sets. And the next result is what? A phi dx is equals to A phi of dx if and only if A greater than 0. So now let's start the proof. So proof number one. So let phi is a simple measurable function, simple measurable function, then therefore we can write integration of phi over e is what? We can just write this is the property. Okay, that we have used here, I think this is the property. This is the property that by the definition third measurable function is if we have a measurable set and we are just integrating some function or measurable function, then it will be equals to the characteristic of the multiplication of the characteristic of the function. Okay, let g is equals to phi and chi of x. I have just taken it as z. Then g of x is equals to phi of x. Characteristic of E is defined as pi into 1. It means the value of characteristic 1 for all x belonging from E. Okay, and it will be 0 if x does not belonging from E. Okay, then again, since phi and characteristic of E both are measurable, and so G be product of g of x be the product of two measurable function, product of two measurable function, then g of x is also measurable function. It means that if x does not belonging from E, then g of x is equals to 0. If x belonging from E, then g of x is what? Just phi of x. Okay. Now, if it is belonging from this phi, or it means what? If x belonging from this, then x belonging from A intersection E, or basically A1 intersection E. We are just taking A1, A2 or all AIs for this, or A2 intersection of E, or A3 intersection of E, or basically what we can write just AN intersection of E. Therefore, g of x is equals to the summation I is equals to 1 to n AI, I of AI intersection of E. Okay, by using the definition, we can just integrate this function with respect to this is summation I is equals to 1 to n of all AI and characteristics, or the measure of, if we take the integration, then it will be the measure of all AI intersection, all AI intersection E. Okay, so it is what G function is pi of chi of E, and we are integrating it over E. Dx is what? Summation I is equals to 1 to n AI, and the measure of all AI intersection. Yeah, you can write it just as EI because, yeah, not EI. Yes, so this is the first result that we want to prove. So this is what the first result here for every measurable, for any measurable set E. Now the second result is what? Result number 2. Since phi is a measurable set, phi is a measurable function, then the union of AB phi of x dx is equals to the summation I is equals to 1 to n. In the previous case, there is a E, and now there is E union B. It means the all things will remain same. A of I intersection A union B only will replace E by A union B. Okay, what will happen? I is equals to 1 to n, it is ai m, and we can just write by the De Morgan's or by the result of the operations are basically ai union b. Okay, now it is what the summation I is equals to 1 to n, so ai and the measure of ai intersection a plus measure of ai union. I think there is also intersection. Yes. No, no union. This is also intersection. A intersection B. Yes. Now it is what the summation I is equals to 1 to. So it is AI M of AI intersection A plus summation I is equals to 1n. It is AI and measure of AI intersection B. Okay. Okay. Yeah. The integration will over that function which is within the intersection. It means it is what the integration over a of I of x dx, and it is what within the intersection that is b. It is over b for what phi of x dx, and it is what a union b phi of x dx. So this is the result number 7. Now we have third result is what a will be constant or a will be greater than 0, then we can write just a at as outside. So the third result is since phi is a simple measurable function, simple measurable function, then it takes values a1, a2 up to an. So a greater than 0 and a5 will be a5 will take a5 will take values a into a1, a into a2, a into an. It means a of phi dx is what? The summation I is equals to 1 to n a into ai and m of ai. It means I can write this a outside. So it is I is equals to 1 to a and ai m of ai. It is what the function phi. So a of phi dx is what? A integration of phi dx. So this is the result that we want to prove. So this is all the theorem and the concept of the measurable function almost everywhere. Thanks for watching my video. Keep watching MH Maths. For more videos, you can subscribe my channel, share the video, like the video. Thank you. Bye bye.